If you want to understand the foundation of reality, you face a brutal structural problem. You must explain where space and time actually come from without accidentally assuming they already exist at the deepest level. For years, the gold standard in foundational physics has been to try and build reality from a purely non-spatial, mathematically abstract subspace. This approach relies on a strict rule we can call the honesty gate. If you are building a foundational model, you cannot smuggle in any pre-existing coordinates, metric distances, or external observers. You have to build structure from pure math. But early phases of this project proved exactly how difficult that is. We found that perfect, featureless mathematical sameness cannot internally generate structural difference. You need some form of inherent distinction to get off the ground. Even if you start with the simplest possible connections, pure pairwise relations, known as dyads, it is mathematically insufficient. Pairwise relation alone does not force a spatial direction, and it cannot independently generate an ordered geometry. Demanding a flawless, complete derivation of three-dimensional space from absolute mathematical nothingness imposes an almost impossible metaphysical audit burden on researchers. The risk here is obvious. Insisting on this absolute standard traps the entire project in an endless loop of philosophical permission-seeking. The physics stalls out before any actual modeling can even begin. To break the stall, the search has to adapt. Physics must pause the pursuit of derivation from absolute nothingness and relocate its working foundation to a point where constructive modeling is actually possible. This brings us to a crucial structural change in the project's methodology. Instead of trying to build reality from completely outside of space, the starting assumption point is now placed securely inside the observed 3D space we already know exists. Within that space, we establish a new foundational unit for reconstructive modeling, the Planckian grain, operating at the extreme boundary of the 10 to the minus 35 meter scale. This diagram illustrates exactly how deep that is. We start at the human scale at 10 to the 0 meters. We drop 10 orders of magnitude to a typical atom, then down to a proton at roughly 10 to the minus 15 meters. Finally, we hit the Planck scale. Look at this gap. There is a 19 order of magnitude void between the proton and the Planck scale. That immense distance proves that our ordinary intuition about how particles behave is useless down here. Because of that, we have to be very precise about our definitions. A Planckian grain is not a tiny solid bead. It is not a rigid voxel of space, and it is certainly not a proven quantum particle. What it is allowed to be is the smallest meaningful structural placeholder capable of carrying local relations. It is the raw architectural seed of physical reality. By treating this grain as our working assumption, we establish a firm footing. We can begin piecing together local rules and building upwards to see if they produce the known physics of the larger universe. Relocating this assumption point is the mechanism that frees the project. It forces the transition out of metaphysical philosophy and into active, testable structural engineering. Because this new starting point exists inside 3D space, our rules of investigation change. Spatial concepts like volume, direction, and density are no longer treated as forbidden contraband. Instead, the spatial phenomena we observe at the macro scale are admitted as empirical guide rails. They define the boundaries that shape and constrain our theoretical models at the microscale. But this introduces a strict new audit burden. We can use space to guide the model, but we cannot explain space by circularly fitting parameters to it, or by simply restating known facts and calling them a derivation. Every structural claim must be earned. The first major constraint is observed 3D locality. Whatever mathematical relations we assign to these grains, they must actively support effective local neighborhood behavior without us forcing it to happen. The next constraint is continuity. This animation shows a field of distinct, disconnected grains. As we zoom out, those discrete units must coarse grain into the smooth, continuous macro geometry we perceive as everyday space. Furthermore, any candidate model we build has to prove it is mathematically compatible with stable atomic matter and causal regularity. And it has to do this without prematurely labeling grains as known forces or fields. The macro world strictly dictates the rules the micro world must follow. This guarantees that our foundational physics remains firmly attached to observable reality, rather than drifting into purely abstract math. With the rules set, we can start testing specific candidate mechanisms. The first is defining grain adjacency. We need to find interaction rules that generate effective locality, but we have to do it without cheating by assuming a fixed, pre-existing lattice structure. To solve this, we introduce the concept of shell-like neighborhoods. In this model, surrounding layers of relational connections form around individual central grains, but these grains don't exist in isolation. Look at this central node generating its boundary layer. A single grain acts simultaneously as a member of many different surrounding neighborhoods, creating intense intersecting zones. These overlapping regions provide rigorous structural constraints. The shared membership locks the nodes together, transitioning the model out from theoretical bookkeeping and into actual, stable geometry. Another candidate mechanism is local anisotropy. This tests the idea that individual grain relations might contain inherent localized asymmetries. If those microasymmetries exist, the model must demonstrate how millions of them either average out or organize mathematically to produce the uniform isotropic space we observe at human scales. Overlapping neighborhoods and structural constraints provide the foundational grammar for this phase. They give us a concrete way to test whether a subparticle architecture can actually generate the properties of three-dimensional space. Building a candidate model is only the first step. The ultimate hurdle of this reconstructive phase is proving the model survives aggressive comparison against simpler mathematical controls. We employ a methodology of deliberate adversarial testing. We actively try to break these models to see if they fall into known mathematical failure states. The first failure is structural collapse, a random graph with no coherent structure. The second freezes into a rigid crystalline lattice, proving coordinates were illegally smuggled in. The target state sits between them, achieving constrained organic geometry without becoming rigidly uniform or totally chaotic. This adversarial testing is our primary filter. It ruthlessly eliminates models that offer nothing more than visual appeal, demanding strictly recoverable geometric structure. Real foundational physics must actively resist degenerating into mathematical trivialities. Every bit of structural complexity must be thoroughly earned. That brings us to the final and most rigorous stress test for any candidate grain model, the 3D scaling test. We have to guard against the mathematical threat of expander-like scaling. This is a fatal flaw found in networks built purely on the number of connections, like 14-15-degree admixtures, where the math expands far too quickly. Here is that failure. The network propagates so rapidly it creates non-physical long-range shortcuts, destroying any local spatial neighborhood. Contrast that with true 3D local scaling. Here, structural relations strictly respect local geometry under iteration. The network grows layer by layer, exactly like physical space. Passing this scaling test is the decisive proof. It confirms the candidate grain possesses actual, recoverable 3D geometry, emerging entirely from its internal rules. This defines the overarching goal of our current reconstructive phase. We are replacing metaphysical permission seeking with testable structural clarity and extreme resistance to failure. By relocating the assumption point to the Planckian grain, foundational physics moves past the philosophical stall. We are actively reconstructing physical reality.